All right. So we moved classrooms, obviously, just check to make sure no one else is down there. Should be able to get everyone in every other class. So there's kind of two groups. This week I had group 1 Wednesday and then group 2 Friday. And then basically just alternates every other class period from there on out. So next week, group 1 would meet Monday, Friday. Group 2 would meet Wednesday. And then the following week, group 2 would meet Monday, Friday. And then so kind of so on and so forth, proceed like that. So if you ever have any questions, if you forget where we're at, you missed a class, I can't remember who's meeting tomorrow, feel free to send me an email, but we've got just enough seats in here to where we can get everybody in every other class, okay? So where we left off last class, we were building some of these frequency distribution tables in Excel. We kind of stopped, I think, let's see where we got into in the Excel file, where we had calculated percent frequencies, okay? So we'll kind of continue with this, introduce a new idea kind of with Excel and kind of by hand, and then we'll kind of move into the next subject, which is that Learn Smart that you're supposed to get done kind of before next Monday, by the end of the week. So that on Monday, we'll introduce some more ideas of central tendency, measures of dispersion on Friday, but really next week we'll start hitting that new kind of subject and material pretty hard. So this is where we left off, right? We had these relative frequencies for each bin, we had percent frequencies. So one thing that we didn't quite get to, I didn't mention, but if we remember that these relative frequencies represent proportions. So the proportion of states that have had kind of COVID deaths in between 0 and 525,000 was about 0.7, or about 70-ish% of the states kind of fit into that bin. Okay? So with that in mind, these relative frequencies, if I add them up, what should they add up to? If I've counted every observation at least once, they should add up to, someone just held up, 1, right? So I hit enter here using that sum function. Sure enough, my relative frequencies add up to 1. Right? I can get rid of this here. If I add up the percent frequencies, what should those add up to? 100%, right? Sure enough, they do. Now, if you ever get to this point, you don't have to do this, but it's a good check to make sure that I've done things correctly, right? If I get anything other than 1 or 100 here, I know I might have made a mistake, okay? So that's just kind of a good way to check to make sure what you're doing is correct, given what we know kind of about what these should add up to. So the next idea that we're going to talk about, let me move this thing out of the way, is start out with cumulative frequencies. Okay? So this idea of cumulative frequencies, right, I think maybe the way I always describe it, right, is that we're going to be looking at not just, right, if I'm talking about your GPA, right, your current GPA would be like your GPA this semester. But your cumulative GPA looks at this semester and goes all the way back in time, right, to your very first class. So it's the same idea with cumulative frequencies. So I've got a marker that works. There you go. Right, if I'm thinking about, I have just a relative frequency graph. So maybe, and it doesn't matter what the bins are. So I'll just put kind of bins 1, 2, and 3. This might be something like, I don't know, 0 to 10, 11 to 20, 21 to 30. And let's say I've got, I don't know, some relative frequencies. We'll put some numbers to it. So this is 5, this is 3, this is 1. Okay? To get my cumulative frequencies, what I'm going to do is take the relative frequency of the bin that I'm looking at and add to it the frequencies of every bin below it. Okay? So let me see where I've got, how much room I've got here. So is this showing up on the video? Yeah. And I'll kind of move out of the way here in a second for you guys on this side of the classroom. So if I'm looking at these same bins, 0 to 10, 11 to 20, 21 to 30, the cumulative frequency for the first bin, right, the kind of definition of cumulative frequency is the frequency of this bin that we're looking at plus the frequency of every bin below it. For that first bin, if we take its frequency and add to it all the bins below it, well, there's no bins below it, right? So the cumulative frequency for that first bin, right, is just its own frequency, right? What about when I go to the next bin? Well, I'll take its frequency and add up the frequency of every bin below it, okay? So I'll take its frequency of 3, add to it the frequency of every bin below it. Well, there's one bin below it, so 5. 5 plus 3 there would be at 8. Cumulative frequency of the next bin. I take its frequency, add all the frequencies below it. So it has a frequency of 1. The bins below it have frequencies of 3 and 5. So basically just add them all up. And I'd have a cumulative frequency of 9. Okay? That's the idea of what we're doing with cumulative frequencies. Okay? Another way to think about this, and once I go to Excel here in a second, this is how we'll use Excel to calculate our cumulative frequencies. Notice, when I wanted to find the cumulative frequency for this third bin, I take its frequency and add up the frequencies below it. What I could have also done is say, okay, to get this cumulative frequency, take the frequency of that bin and add to it the cumulative frequency from the bin right below it. So 1 plus 8 would have still gotten me 9. So why is that the case? Well, because the cumulative frequency of the bin right below it took these frequencies and added them together, right? So that'll be kind of helpful once we get to Excel, kind of thinking about to get the cumulative frequency of the bin that you're currently looking at, you can just take its frequency and add to it the cumulative frequency from the bin right below it, because the cumulative frequency of the bin right below it should add up every frequency to the left. Okay? So that's what we're doing. We can kind of think about how we would do this here with our data set in Excel. Okay? So first you get the cumulative frequency, right? For that very first bin, my cumulative frequency is just what? Yeah, it's just the frequency of that bin, so 37, right? What about the next category, right? I could take the cumulative frequency for the next bin will be its frequency plus the frequency of every bin below it. Well, there's only one bin below it, so I would add that in. Okay. What about the next one? I would take that bin's frequency, add to it the frequency of every bin below it. Okay. So we could kind of continue to do this and we have to type it in every single time, but there's another way we could do this as well. So I'll just do it right next to it just to kind of show we get the same numbers. So for the first one, right, not a lot to do there. It's just the cumulative frequency is the same as the relative frequency for the lowest bin. But now for this next one, remember what I said we could do up here on the board. I can take the frequency of the bin I'm looking at and add to it the cumulative frequency, right, of the bin that was right below. Well, the bin that was right below it, I can think about, you can't quite see the number because I'm in this cell, but remember we have the cumulative frequency here. So I could take the frequency of the bin I'm looking at and add to it the cumulative frequency from the bin right before, right? So that would be what, 07? Now when I copy this down, right, instead of K8 and 07, when I copy it down one here, it should be K9 and 08, right? So when I copy this down, notice it takes the frequency of this bin, adds to it the cumulative frequency from the bin right below it. And now when I copy this down, it always does that. It takes the frequency of the bin I'm looking at plus the cumulative frequency from the bin right below it, right? And that way I only had to type it in once. Otherwise, I'm going to have to go, okay, take the frequency of this bin, add to it the frequency of every bin below, right? That's just going to take a lot more time, okay? So this is going to be kind of the preferred method. So I'm just going to copy this title, and then I'm going to click on this column. I'm just going to delete it because we have kind of this better way of doing that. How would I do the cumulative relative frequencies? It's the exact same process, but instead of adding up the frequencies, I simply add up the relative frequencies. So for the very first bin, the cumulative relative frequency will just be the relative frequency of that bin. Right? Or what's another way I probably could have done this? Well, I would just take the cumulative frequency I found and divide it by what? So I could do it this way, right? Just It's the same as the relative frequency for that first bin. Or I could have taken that cumulative relative frequency and divided it by my total number of observations, right? That's how we get relative, right? So to go from frequencies to relative frequencies, we divide it by the total number of observations. To go from cumulative frequencies to cumulative relative frequencies, we can do the exact same thing, okay? Now, if I freeze this, because I always want to be dividing by the total number of observations, that's one way I could come up with it. Now, if I hadn't calculated these cumulative frequencies and I just wanted to jump right to calculating cumulative relative frequencies, well, that was the same process, right? So for this next bin, I'll take its relative frequency, add to it the relative frequency of the bin below it, or we said kind of the easier way to do this in Excel, add to it the cumulative frequency from the bin right below it. So here we've got 07, oops, nope, not 0, 07, right? And now if I copy this down, oh, what is it? Why did it not like that? Oh, because I selected the percent frequency, right? I actually want just the relative. So I wanted not M8, but L8. Now if I copy this down, it should look a little bit better. So notice either way, we get the same answers. It's just kind of two ways of doing the same thing, okay? Any questions on that? You want to see one of those cells again, or why exactly I did something in a cell? We're okay with that? All right. So notice when we get to that very last bin, I'm getting this cumulative relative frequency of 1, right? Because by the time I get to the last bin, what that's saying is count the number of observations that are in this range plus all the observations in all of these ranges. Well, that covers every possible answer I could see for this variable. So I will have counted every single observation once, dividing by the kind of the total number of observations to get the relative frequency, and I'll get that cumulative relative frequency of 1 for that last bin, okay? Or the cumulative frequency, right, not relative frequency, but just the frequencies. Once I get to that last bin, the cumulative frequency should be the total number of observations, right? Every observation should be counted at least once I get to this last bin, okay? Any questions on that? Okay with that? All right. Why is Excel mad at me? There we go. That's probably all I want to kind of do here in Excel for the moment. We'll kind of go back and forth. I'll show you a couple little things. You know, we could graph these cumulative frequencies as well. So just like we did last class, creating the histograms, we could highlight the labels, hold Control, or on a Mac, hold Command, select my cumulative relative frequencies, go to Insert. Now, typically, instead of using kind of a bar or a column graph for these cumulative relative frequencies, we use a line graph, right? And it's just the option that's right below it. So I go to Insert, a line graph. Now it kind of shows, here's my bins, here's the cumulative relative frequency, right? It kind of slowly is approaching that value of 1, okay? So pretty easy, not a whole lot new there. We're just selecting, instead of the frequencies or the relative frequencies, we're selecting the cumulative relative frequencies. I think the next thing that I have, so yeah, cumulative frequency polygon or cumulative frequency graph. Either way, that's what we can kind of do in Excel there. What if, so up to this point, we've really only looked at one variable, right? Showing the distribution of one variable. A lot of the times we want to know what's the relationship between two variables, okay? So anytime we want to know the relationship between two variables, we'll call that first variable X and that second variable Y. So the relationship between X and Y, we can use a scatter plot, okay? So all a scatter plot does is takes a data set and plots every single observation based off of the X and Y values or whatever values we see for the two variables. So here was a small data set we could use to kind of create a scatter plot. It's got a bunch of different countries. It has how much they're spending on health and what their life expectancy is. So health, I guess, expenditures per capita. So what this is saying is if per capita a country is spending more on its health, does that have any influence or does it look like it's correlated with life expectancy? Okay. So I just copy and pasted this into that COVID data blank file, or as we've been working on it, I've been kind of saving it, and I'll kind of post the completed version after class today that has all this information. So I copy and pasted that data over here in a different sheet, so life expectancy worksheet. Now I'm just going to highlight my data, right? So I've got the names of the data as well here. And then I've got the actual two variables, so healthcare expenditures and life expectancy. I go to insert, I go to over to my graphs, I've got a bunch of different options. I'll hit this scatter plot, okay? Now it kind of uses those as kind of my title. I can change the title if I want, but here I've got healthcare expenditures on my x-axis, life expectancy on my y-axis, and here's every single data point plotted. So at this point, usually we try to think about things like, well, if I was to draw a line through this data, what would best fit it? You can kind of imagine it's probably a slightly positive line. So maybe there is some correlation between the more money spent on healthcare, higher life expectancies we see in those countries. But it looks like also if that line of best fit, you know, if we take in consideration these outliers, it's probably relatively flat. So maybe there's not much of a relationship going on. Now, this isn't like the most obvious one. Some of them, from once you see all the data plotted, it's very clear there's a positive or a negative relationship between those two variables. This one's probably a little bit more vague, but that is the process you would use to just create that scatter plot, okay? And we could add titles to the axis and make this a lot fancier, but this is really, I'm just showing you how to get the data into that graph, okay? Interestingly enough, this is kind of an interesting example, but like if we look at what these countries actually are, notice like there's an outlier here where this country is spending by far the most on their health, but their life expectancy is like second worst, right? Of these countries, of these OECD countries. So kind of interesting. That would warrant a much longer discussion, but this is kind of a fun little data set to play around with. The next thing I want to show you how to do in Excel, once again, pretty easy, similar to things we've already done. Let's say I have the US unemployment rate, and I've got it for a bunch of different years. So actually, this is kind of a truncated version of the one that I put in Excel. In Excel, I have it all the way to 2020. Okay, so I've got, what, 16 years of data here. So a time series graph takes a time series data set, right? One subject, the United States, over various points in time, and we use the years as kind of our X variable, or on our X-axis. We then, for every year, plot the value of whatever variable we're interested in, here, the unemployment rate. Okay? So all I'm going to do, first I'll show you how to do it where it doesn't work. So we highlight the data. We've got our X-axis variable. We've got our Y-axis variable. You would think that if I go and insert a line graph here, it'll just use these as my X values, use these as my Y values. But it doesn't, right? When you use that line graph option, it essentially treats those variables like they're both different variables, and these are Y values, right? So we can't do that, but what we can do, right, is select this unemployment rate variable, go to insert, we'll put a line graph in. So now I've got all my unemployment rates plotted, but I don't know what years these are, right? So the way we fix this, and nobody yelled at me that I forgot to zoom in on this a little bit, and it's probably harder to see. All right. So what we've got here, if I can scroll over, if I click on these numbers, so left click, this little box goes around them. We then right click, go to select data, the axis labels we want, we'll go to edit, and now we just select those years, okay? Once I've selected those years, I'll hit OK, make this a little bigger so that they're not so close. And now I can kind of see I've got my years down here on my x-axis. Yeah. Yep. So the first part is pretty easy, right? You just selected the data, you inserted a line graph, right? From there, you just had numbers down here on the x-axis. So I'll click on them, left click, it gets this like little thin box around them. I then right click in that area, and there's a select data option. So I'll hit select data. Now I've got some things going on here. I'm worried about the x-axis labels, right? The horizontal labels. I want them to be the years, so I clicked edit. And then from there, I just selected the years that I wanted, okay? And hit OK, and hit OK. But the reason why these time series graphs are useful is because it gets a lot of information out really quickly, right? I can look at this graph and tell you a very quick, quick story that gives you quite a bit of information. Mid-2000s unemployment rate was around 5%. It remained pretty steady, then increased in 2008 up until about peaking kind of around 2010. Since then, it's been on a slow decline up until 2019, where we saw this huge spike in 2020. You can kind of imagine why we saw that huge spike, but I can tell that story pretty quickly just looking at this graph. Any other questions on that? So creating these tables or these graphs is pretty easy. The histogram was a little bit more work, kind of using that count ifs. Now, one thing I want to mention, likely after class on Friday, I'll post the first Excel assignment. I'm going to ask you to do a histogram. So I showed you all of this for a reason. A lot of it is like the process helps us learn a lot of different functions. So the idea of using that count ifs, the idea of using kind of that sum function, the maximum, the minimum function, thinking about how we use cell references to kind of save us some work here, like creating the cumulative frequencies. I want you, to learn all the skills that were involved in that process. I'm not saying you would always have to use those to do a histogram. I'll show you in a second. There is a small shortcut. But for future assignments and for future things we're doing in this class, I want you to learn kind of some of these more fundamental functions that we talked about. Right? Also, it's always good to use Excel kind of as we're learning stats, because you can see kind of that you can always do things and find the intermediate steps and kind of figure out what exactly is going on. I'll show you one thing that's built in here. Some people on this first assignment, even though I'm telling you not to do this, they'll select that first variable because they'll Google how to do a histogram in Excel, right? And if you highlight the variable you want to put in a histogram, you go to Insert. There's this guy right here. It says it's a statistics chart. Click on that, and there's a histogram option, right? Now, the problem is with this histogram option, I can't, I can go in and edit things and try to get these cutoff values to be right. I've never seen someone do it correct yet. I mean, I guess I'm not showing you how to do it, so you're kind of on, anyone who's ever tried to do it has done it on their own, even though I said not to. But this way is just, honestly, to me, it's a lot more complicated. You go in, and there's like option, like I think it's, how can you right click and then not chart type. I don't even remember where it's at. So you would go like, maybe it's select data. No, what is it? You can go in, I can't even remember how to do it off the top of my head, but you can go back in and edit kind of what the cutoff values you want to use are, where you want the equalities to be, but it's a lot harder to kind of figure out. It's not as user-friendly as kind of setting everything up the way that we did. Also, it doesn't really give you as much freedom in terms of selecting exactly what you want the cutoffs to be. Notice it doesn't start at 0 here. It's starting at 10,000. The numbers just don't look as clean. And, the other issue with this is if something changes where I want to do different bin sizes, I have to go back through and update every single thing behind this chart. Whereas the way that we did it, we said, if I ever want to change this bin length, let's do something crazy so the numbers will actually change. This won't really be perfect, but all the numbers change here, right? Everything changes, right? From that, just changing one cell. So it's a lot easier if things were to if you wanted to change the histogram you're creating, to change it using this method and all the cell references. But also, I want you to start learning some of these functions that we talked about, okay? Any questions on that? Also notice, if we have it set up this way, it's a lot easier to do these cumulative frequencies, which that built-in histogram tool can't do the cumulative frequencies, okay? All right, so that should cover us for the table and graph stuff. We'll think about a couple more graphs. What am I doing? Whoops. We'll think about things graphically a little bit here and then kind of move in to talking about measures of central tendency. And I don't know if we'll get there today, kind of relating these distribution shapes to things like the mean and the mode. But for sure on Friday, we'll get to finish that discussion, hopefully kind of bring this all together. Right? But for right now, let's just think about we talked about how we can create these frequency distributions. And they tell us where the majority of the data lies, right? When we're thinking about kind of COVID deaths here, or deaths or cases, and depending which one we did, we can see that the majority of states were kind of in this lower range with some states in these higher ranges, right? Or, you know, just give me a quick snapshot of the distribution of the data. So let's think about different distribution shapes we could see. So the one that we're going to focus on a lot during this course, probably not for a month or so, but once we get to it, we'll be talking about it a lot, is the normal distribution, okay? So if I had data, and I think this was the SAT score data, you can kind of see that if I had to trace a line that best fit the tops of these bars, it's going to kind of look like a symmetric kind of hill or a bell. Sometimes you'll hear it called the bell curve. But this is a distribution that pops up a lot, right? Once we get to it, we'll talk about how crazy it is. Like a lot of biological measures all follow a normal distribution. They try to write tests so that they follow a normal distribution. It just pops up a lot, right? It has a lot of nice properties that allow us to do some pretty cool things by the time we get to the end of the semester, okay? But you notice all this is a frequency distribution, right? I had SAT scores from different high schools. Excuse me, I counted up the number of schools that had an average SAT score within this range, then within this range, then within this range. So I basically just did a frequency distribution, right? And here we call this shape a normal distribution, okay? Now it's not perfectly normal, right? There's a kind of a dip here, but if I was to try to draw a line that best fit, it's going to be close to a normal distribution. Here we've got income, right? So I was using this example a lot in just talking last class, but here they've got, it's hard to see, but the number of household, or the percent of households making under 5,000, between 5 and 10,000, $5,000 jumps up until they get to these higher numbers. Now you got like the number between 200 and 250,000. $250,000 and over. So this is where they kept the bins the same as long as they could. And then towards the end, they kind of created these larger and then eventually a catch-all category on the end, right? To make sure that those bins were exhaustive. But notice if I drew a line that best fit the top of all of these bars, right? I can kind of think about it looks like this, kind of like a hill, but with a really long right tail, right? The majority of people were down here in these lower income ranges, but we had a few kind of up here in these higher ranges. So anytime we see this like long right tail, think about, we call that a right skewed distribution. Now the long right tail is not necessarily the reason why. We'll talk about that. Like I said, hopefully we'll get there by the end of the class today, if not on Friday. But for now, you can think about if you saw a distribution where the data has a long right tail, that's a right skewed distribution, okay? We can think of an example where we have kind of a longer left tail. We would call that a left skewed distribution. So something like length of a pregnancy, right? We see premature births. The majority of births are kind of right there around 9 months. And you don't really see, you know, children being born on the right-hand side, like at 11 months, right? So we kind of have this longer left tail for this variable. So the longer left tail, we call it a left skewed distribution, okay? And then kind of the last one, we'll call this one bimodal. It almost looks like if I had to draw a line here, whoops, it kind of looks like almost like two normal distributions, right? So if I'm looking at this variable of weight, body mass, why might I end up with a frequency distribution that looks like this? Yeah, right? There's a marked difference in the average weight of males versus females, right? And so each one, male weight and female weight, actually pretty closely follows a normal distribution. But when we throw them all in the same data set, it almost looks like now we have kind of two normal distributions in one, right? Because we really did, right? We had a characteristic that drove a difference in kind of the average of the variable that we were looking at, or the mean for that body mass variable that we were looking at, okay? Any questions on any of that? I'm just kind of introducing this idea. So the next thing we'll start talking about is actually doing a little bit more computation and calculating some statistics from a data set, right? So I think I mentioned this term that we're going to talk about, but we're going to talk about measures of central tendency. So the distribution is great, right? It's great to be able to see that. But sometimes even without doing that, I just want a statistic that tells me like where's the middle of this data set? Like what's kind of the average response that I see for this variable, right? So we get kind of lazy, I guess. We think of this, you know, the central tendency, we always think of kind of average. Really, the terminology we want to use is what's the mean, what's the median, what's the mode. And those are three different measures of where the center of this data set is, or where the most common responses are, or on average where we would see these responses. So the way that we're going to notate this is we have two different things that we can calculate. So we could have a population data set or a sample data set. So there, if we have a population data set, we'll call this Greek letter mu, right? This is going to be our population mean. So this kind of mu here we'll call the population mean. X bar, right, we'll call, that's the mean from a sample. Sample data set, if we calculate the mean, we'll call that a sample mean. So the sample mean is notated with this X bar. The population mean is notated with this Greek letter mu, right? So anytime we use Greek letters, that's going to be population statistic. Anytime we use like, you know, our kind of normal alphabet, right, that's going to be considered a sample statistic, right? It's coming from a sample data set. That's kind of how we identify that, all right? For the median and the mode, we'll just call, you know, usually, honestly, we're going to write out the word, but if we really wanted to kind of shorthand, capital M with a subscript D is the medium, capital M with a subscript O, that's our mode, right? That's kind of easy to remember, I think. And I didn't put it on here, but if I wanted to find the sample median or a sample mode, the only difference with those two is we do a lowercase m and a lowercase m here, right? M, lowercase m subscript O would be sample mode. Okay. But I'm not going to try to trick you on that, and there's really no difference in the process, so that's why we're not as focused on notating this differently. But once we get into some different topics, knowing the difference between the population mean and the sample mean will become important. Okay. We'll talk about these maybe Friday, more likely on Monday, but measures of variation we'll call sigma squared, right? Once again, we use a Greek letter. This represents the population variance, and then S squared represents the sample variance, okay? The other measure we'll take is the standard deviation. It's really just scaling the variance. Notice we use the same Greek letter here. So sigma is the standard deviation and sigma squared is the variance. S would be the sample standard deviation. S squared is the sample variance. So it's just like we're scaling the variance, right? We're taking the square root of the variance to get the standard deviation. But this will be kind of the notation that we use, all right? Any questions on that? Okay, so if we think about the mean, more often than not, what you probably would call this, or what you've heard people call this, is the average, right? So if I had 5 numbers, how would I find the average? Or how would I find the mean? Yeah, I had 5 numbers, right? So I'd add the 5 numbers up and I divide by 5, right? Or a little bit more technical, if we want to look at the math, right, or think about what we're doing mathematically, we're just adding all those numbers up and dividing by the total number of observations that we had, or the total number of numbers that we had, right? That's all this is saying. Now, we'll start to use the math to kind of understand what's going on behind the scenes with some of these statistics. So with the mean, right, when I write this guy here, this capital sigma, right, this is called like a summation sign. So what it's saying is go from the very first observation all the way to the last observation in the data set. So capital N represents the total number of observations in the population data, okay? So go from the first observation to the very last in the population data set, add up all the values for this variable X, right? Every single observation, whatever value is in there for that variable X, add them all up, and then divide by the total number of observations you had in that data set. Right? Or, you know, if we wrote that summation out, right, we're just adding up every single observation in that data set. Now, the sample mean is the exact same. The only difference is you go from the first observation not to capital N, the number of observations in the population data set, but you go from the first observation to lowercase n, which is how we notate the number of observations in my sample data set. Remember, the sample data is going to be a subset of that population, so it's going to be a smaller number of observations here, right? But the procedure is exactly the same, right? Once you have your list of numbers, you just add them all up and divide by however many numbers you have there, right? No matter if it's a population or a sample data set. So, you know, if we wanted to find the mean birth weight in the US, if I had a data set that had every single birth ever, I would take every weight of every child born, add them all up, and then divide by the total number of births, right? However many births I have in that data set. Okay.
Are you going to want us to memorize like these?
No, so when I show you, when I'm showing you some of these mathematical formulas, some of them we will have to use for computation. I mean, you're going to have to use this essentially in that if I gave you 10 numbers, you could find the mean, right? But I'm never going to ask you to like write it out in summation format or kind of, you know, write out the exact formula on the exam. I'll actually give you formula sheets. So you'll have the formulas kind of on a kind of summarized in a file when you go to take that exam. So it's not like you have to memorize these, but I just talk through them so that we can kind of understand what's going on behind the scenes or the process that we're using, how that's influencing the statistic that we're looking at. Does that answer your question?
Yep, thank you.
So, you know, in the example of this formula, you know, we can think about what this really means, that we're just adding up every observation divided by the total number. Well, then if I have an observation, right, like let's say I'm doing the income thing, right? So I've got a data set with a bunch of different incomes. I want to find the average income. I add them all up, divide by the total number of observations I have. What happens to the mean if one of those observations is something like, I don't know, 30 million? Well, that's a huge number that gets added in to that numerator. So one really big outlier, like 30 million in that data set, could greatly influence that mean, right? But understanding what that formula means, we can then think about how a one very large value might influence a lot. Okay? Okay, so we could get this answer for the mean if we had this data set. We'll actually play around with this data set a little bit once we get to some more topics, looking at kind of this data set that has a bunch of different births in the US. So we'll go through a couple easy examples, I think, for the mean here. I'm not gonna waste a lot of time. I'm sure, how many of you have like calculated averages before, right, in classes? I'm sure almost every single person. So if we want to find the population mean, here's our data set. Doesn't matter what game this is. I don't know, could be basketball, could be boggle. I don't really care. But we've got 7 games. Here's the number of points scored in each game. What's going to be the mean points scored? So if I had some, you know, if I wanted to do this, I would add all these values up and then divide by the number of observations I have, right? So just add up all these points scored, divide by that total number of observations, which here I have 7 games, okay? I don't think that's too bad, but I want to go through another question and start to just think about the principles behind the mean, okay? So let's say I had a very similar data set, but now I've got employees and their commute time. So 7 different employees, how long it takes them to drive to work, right? I wanted to find the mean here, and I gave you these answers, right? You can start to think about, well, actually I'm going to change these because I wanted to point something out, and I thought one of these was going to be different. So let me go, let's do this, and let's do, you can already see the answer, but that's okay, right? So let's say these were the possible answers you were given. Now I changed them so you can probably guess which ones you can rule out, but which ones can I rule out right away and why? Right? Yeah. What do you mean by it's too low?
There's a 90, a 45.
Yeah.
50, find the average.
Yeah, so you're looking at this and saying a lot of the numbers are much higher than 15. So if I'm looking for the middle point of that data set, if all these numbers are way over here, higher up on the right-hand side, how would I get a mean? How's the middle at 15? But I actually can go even further and say I can rule out 15 because not only are a lot of the numbers greater than 15, all the numbers are. So how can I get a mean that's outside the range of my data? That doesn't make any sense. I'm looking for the middle point, right? So anytime we see something that, you know, if you're given an option for the mean, the mean has to be in between your minimum and your maximum, right? It's the middle point, so it has to be somewhere in between there, right? Now, so we could rule out A because it's higher than all the observations. C's lower, so those can't be our measure of central tendency. So this is where don't get too lost in the formula. If you like had accidentally, I don't know, divided by 5 or 6 because you just hit the wrong button on your calculator. I do that all the time using the calculator. You should see the answer right away and go, oh, there's no way it should be 15. I must have made a mistake, right? Just kind of briefly looking at this data set. Now, whether or not the answer is B or D, we probably can't distinguish from just looking at the data there. Probably actually have to go ahead and compute it, right? But, kind of remembering what you're calculating, not getting too lost in the formula, because if you get too lost in the formula and you hit a wrong number on your calculator and you don't even think about and just write the number down, you could be wildly off, right? But remembering what you're trying to get this measure of where the middle of the data set is, right? That kind of helps you think about around what it should be. Right? So sure enough, if we add up all these values, so add up all the commute times, divide by the total number of observations, we get 45. Okay. Got what, 8 minutes? Okay, so we'll go through the other two. So the median and the mode. The mode is just the number that happens the most in the data set, right? So if I go back to something like this, what would the mode be here? This was actually pretty easy. There's only one number that happens more than once, which is 35. So the number that happens the most would be 35. That's the mode, okay? Now with small data sets, the mode isn't as interesting because you can imagine with a small data set, what could happen? Well, I never see any number repeated, right? It's from that commute time one, I very easily could have seen 7 different values, right? When we start dealing with larger data sets, it makes a lot more sense to calculate the mode, figure out which value occurs the most in that data set. And if we did something like a frequency distribution, it would be like whatever has the highest bar, right? So the median, right, is a little bit different than the mean in that we're still looking for this measure of kind of central tendency. Where's kind of the most common response? What's the average response? But we actually want to get the value that's, if we ordered the data from smallest to largest, the median is what would be exactly in the middle of those observations, right? So when we're lining them up from smallest to largest, we don't care about the gaps in between each value. We're just thinking about where's the middle placeholder, right? What's the middle place, right? So if I, example, had 101 observations and I had them lined up from smallest to largest, I'd cross off the smallest, I'd cross off the largest value, cross off the next smallest, and then the next largest value, cross off the next smallest, and the next largest, until I get left with that value that would be in that 51st spot, right? The location that would be exactly in the middle of that arranged or kind of sorted data, right? So if I get to that middle place, there should be 50% of the observations to the left, 50% of the observations to the right of that value, right? I can't guarantee that with the mean, right? Because when I calculate the mean, we talked about, if I had a really high value here, that's going to greatly influence the mean. When I'm looking at the median, well, I said, once I arrange them, I'm just crossing off the values. It doesn't matter how high those values on the right are or how low the values are on the left, they just get canceled out. And so they're not influencing the mode near as much as they would the mean, right? And we'll see that with some sample data sets here when we talk a little bit more about this. So how do you find the mean? If it's odd, it's easy. You just use that process of kind of crossing off the highest and the lowest until you get to that last, the value that's left in the middle. If it's even, you'll have 2 values left in the middle, right? If you can imagine if it's, if I had 4 numbers, I cross off the highest, cross off the lowest, the middle 2, right? I'm gonna be left with. Because I cross those out, I have no more values left. So if it's an even number data set, I get down to these last 2 observations, and then I just take the mean of those last 2 observations, right? And we'll work through a few examples here and get some practice with this. So if I think about here, what's the mode for points scored? I already kind of mentioned this in describing the mode. The only number that happens more than once is 35, right? So that one's pretty easy. What would the median be? Well, here I don't have them arranged from smallest to largest, but in a small enough data set, I can probably look through it quick and do that. So cross off the lowest, which looks like is 15. Cross off the highest, which is 35. Oops, here we go. Cross off the next lowest, which is 16, next highest, which is 35. Cross off the next lowest, which is 18, next highest, which is 28. And I'm left with the value that's exactly smack dab in the middle. If we go back here, right? So here was my median. 1, 2, 3 of the observations are below it. 1, 2, 3 observations would be above that value. So 50% of the data is on either side. Okay. Any questions on that? So we just cross off the highest and lowest until we get that middle value. Now we can do this by hand. If I had a large data set, this is tough, right? So we'll talk about next class ways we can do this in Excel very, very easily, right? Because I don't want to do this with a data set of 2,000. I'm getting towards the end here, so I think I'm gonna get 3 minutes. So we'll end with this, right? We'll kind of pick up this discussion next class. But let's think about if I had 1, 2, 3, so that would be, now let's say I have a data set that looks like that, right? What's the mode of this data set? I cross off the highest, cross off the lowest. I'm left with these two in the middle. If I have an even number data set, I said I took the average of those two. So here I'd have a mode of what? 2.5. What's the mean? Well, I add these up, divide by the number of numbers I have. So 1 plus 2 plus 3 plus 4 is 10. Divided by 4 numbers, I would have kind of this mean of 2.5. Right? Yeah.
Wouldn't there be no mode and 2.5 would be the median?
Sorry, you're right. I said mode. I didn't mean that. Thank you. Median, right? I did the process of the median and was saying mode the whole time. So yeah, 2.5, we have the median, 2.5 ends up being the mean. What if I had a data set that doesn't look a whole lot different, but one of the values is really high? What's the median of this new data set? Still 2.5, right? The median's not impacted by these extreme outlier values because they just get crossed off, right? We're just looking for the point that 50% of the data is on either side. We don't care how far away from that middle the data is, right, with the median, but what happens to the mean? Well, now we've got, what, 106 divided by 4, so what, 26.25, I think.
It'd be 26.5 because half would be.
You're right, 0.5. Thank you. I'll tell you right now, my mental math is not always perfect. I try to do it quickly, and sometimes I'll be a little bit off, right? But you get the idea. It's a lot higher, right? The mean is greatly influenced by these outlier values, while the median isn't. So especially when we have small data sets, we probably don't want to rely on the mean as much as the median. Now, with larger data sets, even one extreme outlier, well, if we've got 2,000 other observations, it doesn't carry as much weight. Right, and as we start to talk a little bit more about the variance and the mean, we'll kind of think about kind of weights that don't look like there's any weights when we calculate the mean, but there actually are. So we'll kind of pick up on this discussion next class. We'll talk about how the mean and the median, this idea that they're influenced differently by outliers, leads to those distributional shapes that we talked about earlier. Okay? Get that next Learn Smart assignment done, just get it out of the way. I'll post an online quiz after my next class, so at 2 o'clock. Should be some easy questions related to what we talked about today. I'll probably have you calculate a mean, something like that, but it should be pretty easy points if you get on and get that done before class on Friday, okay? All right, we'll see you guys.